Welcome to the review session for ECE 340. Hopefully we're being recorded, who knows. This is the same process that I just mentioned a couple of hours ago as far as what you are allowed to have. 2 sheets of notes, front and back. Table 4.1, and you can download that. If you don't have a copy, that should be on the D2L website. You can bring a calculator and writing tools. I have the normal office hours scheduled on Wednesday and Thursday mornings from 9 a.m. to 11 a.m. and that's just right around the corner, and I'm probably going to mess up if that's the wrong room, but hopefully you can find me. It's on the syllabus if that's the incorrect room, room 523 or somewhere in that vicinity. You should be able to find me. The topics for the exam: we will have convolution, Bode plots, S-domain equivalent circuits, and you might, for a more extended listing, check the list of topics on D2L. State space representations. Now, some of the earlier exams or practice exams had problems dealing with state space representations and going back and forth between different representations. We haven't yet gotten there this semester, so you won't have to worry about all integrator block diagrams for this exam. That will be the next exam. But with respect to state space representation, you should be able to, given a set of differential equations, if they're coupled and kind of mixed up, you should be able to put those or convert those into a standard state space form. That's what I'm wanting you to be able to do. For the Laplace, you'll need to be able to both do the forward and the inverse Laplace transformation. I may simply ask you to identify the structure, and hopefully that's clear by this point in the semester. If I just say structure, you don't have to solve for all of your coefficients in the expression for, let's say, y of t. You just need to identify the terms. The terms would then be the damping amount or the exponential decay and the damped oscillating frequency. Those are arising from the poles of your expression or your transform for capital Y of S. You need to be able to know what that structurally translates into, those pole locations. I've also had somebody say that some earlier exams might have had the limit as t goes to infinity of little y of t. That's the final value theorem. That's a transform relationship of the Laplace transform. I'm expecting you to know. You should be able to do the initial value theorem or the final value theorem for Laplace transforms. This may not be directly related to Laplace and inverse Laplace, but if you were performing a MATLAB simulation, this is sort of the MATLAB question that I could ask. If you now have an expression or a transform based on those pole locations or based on those forms or the structure of the little y of t, can you now tell me how fine you need to sample and how long of a time window or time horizon should you be running that simulation for? Those are the kinds. So how fast and how long? What's the sample period and what's the duration, or capital T sub n? You also should be expected to answer questions on stability in terms of bounded input, bounded output stability, and asymptotic stability, and know the difference between those types of stability. And I think I'll go through some questions dealing with these latter parts first, and then we'll get into maybe a convolution or a Bode plot or something that I hope you already are pretty comfortable with. Are there questions before we get started on what you might have run across or think you want to have answered before I get started on sort of a canned piece of material? And I'll try to give you something that's a little different than the practice exams. Question? So the asymptotic stability, let me see if I can give you an example. Suppose, and this will be maybe slightly different than what you're used to seeing, but let's just do the following. Suppose that I gave you the following equation. So here we're talking about stability and the difference between BIBO and asymptotic stability. Let's say that I gave you the following system. Y double prime of t, which means the second derivative of y with respect to time, plus y prime of t minus 2y of t equaling x prime of t minus x of t. And now if I called that, let's say, equation A, is equation A, or the system described by that second order differential equation, is it BIBO stable? And is it asymptotically stable? And hopefully this will help clarify what the difference might be with respect to asymptotic stability and bounded input, bounded output. One way to think of this is the BIBO is related to an input-output relationship. It's what's the system between an input and an output, and you're interested in the stability between that set of signals, the input signal and the output signal. Asymptotic stability, on the other hand, is really more worried about the internal stability of the system, independent of how it's interconnected with the input and the output. Meaning you might have a circuit, and the way that you are injecting an input signal and measuring an output signal, you may not have the ability to see all the dynamics between that input and the output. And you might then say, what's the BIBO stability of that system? Well, that may be different than the asymptotic stability, where the asymptotic stability is involving everything in that system, not just what you're seeing between the input and the output. Now, is it clear how you might approach this problem? If I gave it to you right now and I said, here's problem one, part A is the dynamic system BIBO stable for 10 points. For another 10 points, is it asymptotically stable? How would you proceed to address that, or how would you solve that problem? Pardon? You would probably start looking at the transfer function. That's how we're used to seeing it. And the transfer function now says, let's just Laplace transform, and we don't really need to worry too much about initial conditions. If we now Laplace transform that, we would have this s squared plus s minus 2 all times y of s, and that's equal to an s minus 1 capital X of s. And here's where the distinction is going to arise between input-output, or BIBO, and asymptotic. In asymptotic, you're really interested in the dynamic behavior of the entire system, or that stability determined by the characteristic polynomial. If we call this characteristic polynomial Q of S, Q of S now is going to be what we use for asymptotic stability. Meaning now we simply find the roots of Q of S, the characteristic polynomial, and we say, are all of those in the left half plane? If they are, our system is asymptotically stable. Pardon? So now what we have is we have the system stability, just the generic system, and that's what asymptotic stability basically governs. Then we have input-output stability, which is BIBO stable, and there you could have pole zero cancellations that cancel an unstable internal mode that you don't see between the input and the output. It's not something you really want to design or have because it's going to burn up. You're going to have a bad system if you have an asymptotically unstable system. But this is just a theoretical concept to get you thinking about what is possible. In terms of the asymptotic stability for this system, we're now looking at s squared plus s minus 2, or the roots thereof. And maybe, maybe not. Hopefully it's clear that those are the roots or the factors of that second order polynomial. It can be factored into two real roots. And where are those located? We have one at a value of s equal to plus 1. That's actually a pole in the right half plane, and that's a bad pole, right? And we have another pole at minus 2. That one's okay, but if we have any poles in the right half plane, that's a problem. And because of that, this unstable pole is saying that the system is not asymptotically stable. That particular system, governed by those dynamics, that one's not asymptotically stable. But that doesn't say anything about the BIBO stability. So now if we say, well, what about the input-output stability or the BIBO stability? This is now where we have to worry about possible pole zero cancellations. We had the system that was s squared plus s minus 2 times y of s equaling s minus 1 capital X of s. If we now find the transfer function associated with that system, which is what we need to assess BIBO stability, is it clear how to find that y over x? We can multiply both sides through by the factor that's multiplying y of s, or we can divide through that expression. And we can divide both sides by capital X of s, and we end up with s minus 1 over s squared plus s minus 2. But now remember what we said that denominator factored into. And from an input-output perspective, you don't see that bad mode. You've wired the output, or you're measuring the output from that circuit in such a way that you don't see that bad pole at s equal plus 1. And consequently, in an input-output sense, this system would look like 1 over s plus 2. If that's the case, this system is now BIBO stable, even though it was asymptotically unstable. Question?
So we can't get excited the way maybe go non-linear off the rails or anything like that
From an input-output standpoint, this system is theoretically well behaved. As long as no one energizes or puts any initial condition on that unstable pole, then from an input-output perspective, we're okay. This, as long as you hit it with a bounded input, you're going to get a bounded output. In practice, I wouldn't trust it, because anything that you inject into this system is going to excite that mode. And even though you can't see it or measure it at the output, it's there and blowing up. Even though you can't see it, let's say, from that voltage or that current that you're measuring. It's burned your system up, and in a few minutes it's toast. Well, but I thought I had a BIBO stable system. Well, you might have, but It wasn't asymptotically stable, and so you lost it. Yes. It's usually done the other way. Usually, except the one example that the textbook gave you where they had an improper transfer function. Usually, if you have an asymptotically stable system, then you have a BIBO stable system. Usually, that's the implied direction. You usually go in that direction. So if you look at your characteristic polynomial and you find all of its roots are in the left half plane, you can be assured that the BIB, your input-output stability will be guaranteed if you have a strictly proper transfer function, which means the numerator polynomial is strictly less than the denominator polynomial in order. So now is the asymptotic here for I'm sorry, I think the book goes ahead and says anything on the imaginary axis is okay for asymptotic stability. And the way to think of that would be to say, I'm only exciting this with initial conditions. And so in the textbook, I would have to go back and double check this. I don't like that because it's marginally stable, because you can find a bounded input that will drive that system unbounded. But if you just energize, if you had a system that had poles right here, and you said, is this system internally stable? Yes, it is, because if you just energize those, and if you don't excite it, you just energize it, they'll just sit there and oscillate forever. It won't go unbounded. So that's not asymptotically stable, is it? It's just bounded. So I would say let's just say that this is not going to give you an asymptotically stable system. So what they are saying, so if they're saying that this is going to be allowed, meaning that this will just shake and never blow up, what they're suggesting is if you had double poles on top of each other, then that's going to give you this unbounded behavior. Meaning if you now had, if this is now at J1 and minus J1, if you had a G1 of S that was S minus J and S plus J, this now is going to be this S squared plus 1. That they're claiming is bounded. But if you now had a G sub 2 of S that had those repeated, now you would have an S minus J squared and an S plus J squared, or you have S squared plus 1 squared. Then if you inverse transform that, that's got that S squared in the denominator. That gives rise to a T and an unbounded oscillating behavior. And that's what they're meaning by if you just have a single pole on the imaginary axis, we'll say that's okay because the output will be bounded. But if you have multiple poles at the same location, that gives rise to something like this that now has this T when you inverse Laplace transform it. My main concern for you, I think, as a class, is to understand this concept of BIBO stability, meaning asymptotic stability. Let's just worry about checking the characteristic polynomial and making sure its poles are in the left half plane. Then they have these decayed exponents, e to the minus something. That's asymptotically stable. For BIBO, you have to find the transfer function, and you could possibly have unstable factors being canceled, and it would be BIBO stable, theoretically. That's the distinction I want you to be able to produce or use in this class. The others are pretty subtle points. Other questions on BIBO stability and asymptotic stability? What if I gave you another problem that's somewhat related? Suppose that I said, but this is more, well, maybe I don't want to give it away all the way. Let me see if you can think your way through it. Suppose I gave you the following problem. I said if x of t is 3u of t, then I want you to find, let me say, the limit as t goes to infinity of y of t when your system between the input and the output is governed by y triple prime plus 4y double prime plus 14y prime plus 20y of t equaling 4x prime of t plus 5x of t. Any ideas how we would approach this problem? The solution that was proposed is correct. Did everyone understand it? Basically, you transform this differential equation and obtain a transfer function. Then you transform the input, and what's the transform of little x of t? That's 3 over s, isn't it? So you now multiply the transfer function times capital X of s, and you get the Laplace transform of the output. So you would Laplace transform this set of equations, and you now get y of s over x of s equaling h of s. Then you take x of s, which you just said was this 3 over s, and that now allows you to find capital Y of s, which is h of s, x of s. Then you would need to factor the denominator and look to see what's the partial fraction expansion's coefficient associated with the pole at the origin, or the s term. And you're going to have at least one because of this excitation. You're hitting this with a constant input. That's a correct approach, but you could actually solve it without having to factor the denominator if you see that the system is stable. You could use the final value theorem. So you'll have to find the transfer function, but then you wouldn't have to factor anything. Let's find the transfer function for this system. So now we have this y triple prime. We now have s cubed plus 4s squared plus 14s plus 20. All of that is times capital Y of s. And the right-hand side was 4s plus 5, all times x of s. So that now you have this capital H of s is equal to 4s plus 5 over s cubed plus 4s squared plus 14s plus 20. And now if you're not going to factor it, you actually have to be told, is this system stable or not? You could factor it, and with most of your calculators, you can probably do that rather quickly and find that you do have all of your poles in the left half plane. Or you might be told the system is stable. Now, what I was thinking you could do is you could simply find y final value, which is the limit as t goes to infinity of y of t, by the final value theorem. That's the same as the limit as s goes to 0 of s y of s. And that's maybe quicker than doing the partial fraction expansion and finding that one coefficient. Meaning for this system, we're now looking at the limit as s goes to 0 of s. And what is y of s? Well, that's just h of s times x of s. We found h of s. And that's times now this x of s. This s cancels that s, and now we simply let s go to 0. And we're assuming, unless you factored this and found, on an exam, if you didn't have the right calculator, you could just say, I'm going to assume that that factor is stable. And given enough time or energy or other given MATLAB, you could make that check. But here you're showing the thought process, and the thought process is correct. If this is now stable, now you let s go to 0, and you have 4 times 0. I'll do it in a lot of detail. That's the numerator. And downstairs, you just have a bunch of zeros. You have 0 cubed plus 4 times 0 squared plus 14 times 0 plus 20. You're left then with 5 times 3, or 15, all over 20, or the final value for that system that's governed by this third order differential equation is 3/4. And that didn't take a lot of effort if you knew that characteristic polynomial was stable. And that's how you could use the final value theorem. And maybe that's what somebody had seen on an old exam when they were saying, what is this limit as t goes to infinity of little y of t? That's the final value theorem. And I'm expecting you to know that. That's, let's say, part A. Maybe part B says with the same system, find y of t for all t greater than or equal to 0 if x of t is now e to the minus 4t. And maybe now you're told that that transfer function that we started with, which was 4s plus 5 over some cubic, but now I'm going to go ahead and factor that cubic as s squared plus 2s plus 10 times s plus 2. Maybe you're given that now, or you say this system leads to the following transfer function, so that you don't have to rely on having a fancy calculator to factor that cubic. Now you just have to be able to factor quadratic factors. Now, what is, and you should be able to find y of t, the full solution, not just the structure, but y of t. What do you have for that? Well, now you can simply find capital Y of s. That's h of s times x of s. which is 4s plus 5 all over s plus 2. And this quadratic, is it complex roots or real roots? Can you see that? B squared is 4 minus 4ac minus 40. That's a negative number. You know this is giving you complex roots, and you can actually factor this as an s plus 1 squared plus 3 squared. And you also have the capital X of s giving rise to that factor, which says that you could now write this as a over s plus 2 plus b over s plus 4 plus, and you could do this many, many different ways. You could maybe say, oh, I'm going to do that with complex numbers. I'm going to say that's alpha over s minus, how do I want to say this? S plus 1 minus J3. And then I have a plus alpha star S plus 1 plus J3. And now you would want to then find alpha, which is going to in general be a complex number, and you can find A and B. Is that clear? You don't have to do it that way, but yes, so you could write this. So this is all the different lines of line 10, the A, the B, the C, the D. You could have said, oh, this is A, S plus 2 plus B, S plus 4 plus C, S plus 1, S plus 1 squared plus 3 squared plus D times 3, S plus 1 squared plus 3 squared. And then you could find A and B are going to be exactly the same, but now you're looking for a C and a D. And if you found C and D, your Y of t would now be this A e to the minus 2t plus B e to the minus 4t plus C e to the minus t cosine of 3t plus d e to the minus t sine of 3t, and that's true for t greater than or equal to 0. If you did it the other way, you would still have the a and the b the same, but now you have 2 times the magnitude of alpha, e to the minus t cosine of 3t plus the angle of alpha. And that's exactly the same answer as the previous one. It's just the magnitude of alpha and the angle of alpha are related to capital C and capital D in an appropriate way. But I'll accept any of those solutions. And those are different lines of line 10 in table 4.1. And it's really whatever approach you want to use is fine. Questions on that? And actually, I went ahead and solved that. If you're wanting to check your work, maybe you can see if I did it right or wrong. I ended up with y of t being equal to minus 0.15 e to the minus 2t plus 0.3056 e to the minus 4t plus 2 times 0.1496 e to the minus t cosine of 3t minus 121.3 degrees. So a very clean set of numbers. And that you may end up with something like that. And that's true for t greater than or equal to 0. Questions on that? What if I ask you to find a state space representation? And maybe I tell you, okay, here is a coupled set of equations where z's and w's are just generic variables. And I'm not telling you what the state variables are. You have to define those yourself. Meaning, suppose I say, okay, here is a set of coupled differential equations, z double prime plus 2z prime minus 4z plus w of t minus x1 of t is equal to 0. The x's and the y's will be inputs and outputs. But the z's and the w's, they're variables, and those are somehow related to states. Another equation that's coupled into this is w prime minus z prime plus 3x sub 2 of t is equal to 0. And maybe you're told that y sub 1 of t, one of your outputs, is z prime of t, and another output, y sub 2 of t, is w of t plus x sub 2 of t. And now I say find a state space representation for this set of equations. How many q's do we have? How many state variables do you expect to have? Any idea or any way to approach this? We really haven't talked about this, but I'm hoping you get it before the exam. And there's a different problem on the practice exam that will hopefully help you also. Here you have a second order coupled differential equation and a first order. And they're coupled to each other. So really you have a second order and a first order. This second order effectively is two first orders. And you have that w prime, another first order. So you should be expecting a third order system. And the way to do it, a sort of turn the crank way to do it, is solve for the highest powers of your derivatives and then just start assigning state variables. So let's do that process. Let's now solve for the highest derivative of the different variables. Let's solve. Meaning, if we now go back to that z double prime, let's put that on the left and everything else on the right. We now have a z double prime is equal to minus 2z prime of t plus 4z of t minus w of t plus x sub 1 of t. And we also have the w prime equation. The w prime of equation, if we solve that for its highest derivative, that's z prime of t minus 3x sub 2 of t. Those are now our two equations. And what's our state space representation? Our state space representation needs to be derivatives of q. And we only want to take one derivative of q. So we have q sub 1, and if we assign a state variable to be q sub 1, then we need to find an equation for q1 prime. If we assign a state for q sub 2, we need to find q sub 2 prime's equation. If we find q sub 3, then we need to find a q sub 3 prime equation, and those need to be written in terms of q's and x's, and those will be our states. Doing that, let's start the process and say, okay, I don't know where I'm going. Let me just say that q1 is z of t. And now I just keep assigning states, state variables, until I get to the end of the line, which is to say that if I differentiate this, I end up with this highest derivative. Meaning, if I differentiate q1 prime, I get a z prime. I haven't gone far enough, have I? Because I need a z double prime. Which means that let q sub 2 be z prime. All right, now, if that's what DARP wants to do, let's do it again. Do we need to go that far with q sub 3? No, because if we now differentiate q sub 3, we'll get a z triple prime, and we didn't have a z triple prime. So we don't need to go that far with q sub 3. Let's now quit that. Say nope. But do we need a q sub 3? Yes, because we need to, when we differentiate another state variable, we need to get a w prime. But now, if we differentiate these, q1, q2, and q3, we will end up with finding expressions that are on the left-hand side of that equation. Is that making sense? What is q1 prime? q1 prime of t, and this one kind of confuses people. That's z prime, but we've now defined that to be one of our state variables, which is just q sub 2 of t. And that now gives us one of our state equations. We have q1 prime in terms of q1, q2, q3, x1, x2. It's actually only a function of one of those, which is q sub 2, but we're done. We now have a q1 prime equation. What about q2 prime? The way we defined q sub 2, that's just z double prime, but we've now found that to be this four-termed right-hand side. And let's now see if we can replace all of these pieces with state variables. And we can. We now can say that q sub 2 prime is z double prime, but that's minus 2 z prime. But z prime is q sub 2. Is everybody following what I'm trying to do? Then I have plus 4z, but z we defined as a state variable. That was q sub 1. We then have plus 4 q sub 1 of t. Minus w, but w we defined as one of our state variables. So that's minus q sub 3 of t. And finally, we have our input, which is plus x sub 1 of t. Now we have q sub 2 prime as a linear combination of states, q1, q2, q3, none of their derivatives, and inputs. What about q sub 3 prime? That was z prime, but z prime we have in terms of a state variable, that's q sub 2. And the other term is just an input term. Is it clear now what our state space dimensions need to be in terms of matrices? What's our system matrix? How big is the A matrix dimensionally? It better be square, doesn't it? And it's 3 by 3. It has 3 rows to give us something compatible with Q1 prime, Q2 prime, and Q3 prime. And now we can build that up. We can say Q1 prime, Q sub 2 prime, Q sub 3 prime is equal to and then I'm going to have a plus a B matrix times the input vector. How tall is the B matrix? How many rows is the B matrix? It has to be 3, right? And then how many inputs did I have? How many x's did I have? I had 2, so it has to have 2 columns wide. B is now 3 by 2. And we simply need to fill in the numbers. The A matrix, what's the top row of the A matrix? Does everybody see that that's 0, 1, 0? What's the top row of the B matrix? There is no input, but there are 2 inputs, and so we have to cancel both of them. 0, 0. What about the second row? Now this is the more interesting one. What's the second row of the A matrix? Everybody hear that? Should be 4 times Q sub 1, and these aren't written in order, are they? So it's the coefficient of Q sub 1 in the first column, the coefficient of Q sub 2 in the second column, that's our minus 2. Then if we have a Q sub 3 coefficient, which we do, that's going to go in the last column of the second row. Do we have any input? We just need to include x sub 1 with a scaling factor of 1 and no x sub 2. This now, second row becomes 1, 0. What about the third row of the A matrix? And the third row of the B matrix? Your A matrix then, I could just have asked you for that coupled set of differential equations. What are the dimensions of your system matrices, of your state space matrices? B is 3 by 2. What's the output expression going to be? How many rows does the C matrix have? How many Y's do I have? 2. So I better have 2 rows in my output matrix C. And how many columns? It has to be compatible with Q. And now I will add to that a 2-row, and how wide is my D matrix? It has to be as wide as the input vector is tall. So it's 2 TWO wide. The C matrix is then 2 by 3, and the D matrix is 2 by 2. What's the C matrix? Wow. Y1 is Z prime, but Z prime, we'd already written that as a state variable. So Y1 is Q sub 2, isn't it? The top row then of the output matrix needs to pull off Q sub 2 and only Q sub 2, and it has no inputs. That's now the top row of C and the top row of D. The second output equation, Y sub 2, is W, which we define to be Q sub 3, plus X sub 2. Meaning we now have our C matrix is 0, 0, 1, 0, 1. Is that okay? Now what do we do? Do you want to do a Bode plot or convolution? Pardon? Oh, thank you. So I'm falling asleep. So this should not be Q sub 2, should it? This should be Q sub 3. Is that what your question was? That was it the same up above? Wow. I fell asleep a long time ago. I'm just sleeping through this review session. You don't want to sleep through the exam though, okay? Is that okay? I'm not doing this to confuse you, but I'm glad you're catching it. What did I hear? Bode plot or convolution? Bode? Let me see if I can find an example. Let's say, did I hear Bode? Is that what you're saying? Suppose somebody gives you the following transfer function. Pardon? Well, they're both on the exam and they're both worth the same amount of points. So whatever the exam ends up being tonight or tomorrow, whatever mood you guys leave me in, will determine how challenging the exam is. All right, here's our system. H of S is 5S plus 10. So you better hope I have a good dinner tonight, huh? S plus 0.1, S plus 2. We talked, I think, today in class about limiting behavior or the characteristics. Just to give you a little bit of a taste of what the answer in the back of the book might be. Meaning, if we had low omega or low frequencies, what's the magnitude of this going to be for small omega? Is it going to be constant value? Are we going to be coming in flat from low omega for our magnitude? That's what I'm wanting you to sort of see just by looking at the transfer function. That pole at the origin is causing us a problem in terms of low frequency. It's not a problem. It's just giving us nice, different behavior at low frequencies. In particular, we have a very large magnitude at low frequency, don't we? So we're coming down. We're sloping at low frequencies in our magnitude. That's what we should anticipate. What's the phase at low frequencies? It's minus 90. We're starting our phase then at minus 90, and we're going from there, up or down. What's happening for high or large omega? Or in this, what you're wanting to look at now is what I call the pole zero excess, or how many more poles do you have than zeros? And in this case, you have 2 more poles than zeros, or what I call the pole zero excess is 2. And what does that mean for the magnitude? Do you know anything about the magnitude behavior at high frequencies based on just the pole zero relationship or the pole zero excess? It's now going to be going down like you had just 2 poles in your system at high frequencies. And 2 poles contribute 2 times minus 20 dB per decade. Your magnitude then is going to be sloping at minus 40 dB per decade at high frequencies. That's how you could check your resulting Bode plot. This is the answer in the back of the book. What do you know about the phase? Where is the phase going to end up for high frequencies? It's going to have 2 more poles than zeros, so you now effectively have a 2-pole system at high frequencies, and 1 pole contributes minus 90. You have 2 of those. You should be expecting your phase to approach minus 180 at high frequencies. Is that clear? And that's all just by looking at the general behavior or general structure of this transfer function. Now we want to sketch the Bode plot. What do we do? Probably put it in time constant form. So let's start factoring things. We now have h of s. We have a 5. We have a 10 for our 0 factor. Downstairs, we had the pole at the origin. We had a pole at 0.1. We had another pole at 2. And we're getting close to getting what we need. We have 2 into 10, so that gives us 5. We now have 25 divided by 0.1, or we have 250. We now have 250 s over 10 plus 1 all over s over 0.1 plus 1, s over 2 plus 1. And sometimes I sort of like to know the order of what I should be seeing in the overall behavior. I have a pole at the origin. I have my next break is going to be caused by the next frequency that I come to, which is 0.1. This pole at the origin is in effect for all time, or for all frequencies, isn't it? It's going to be sloping. And typically, if we just drew it by itself, it would be going through 0 dB at omega equal to 1. This guy is actually going to kink before omega equal to 1. And that's what I want you to be comfortable thinking about. Even though this pole at the origin is sloping, now it's sloping for low frequencies, but at 0.1, before we hit omega equal to 1, it's going to get a kink, and it's going to start sloping even more than it was. Then what do we come to next? Well, we come to this next pole. By the time we've reached this point, we're now sloping at 60 dB per decade, because we have 3 poles in effect in our magnitude before we even get to our 0, and this will back off on the slope by 20. So we'll be going eventually down at minus 40 dB per decade, which is what we thought. Is that clear? And then the constant, this 250, will raise the whole thing up. And what I would maybe do is I would just say, let me start, well, I don't know. I actually write down my Bode plot before I even start drawing it, just so you kind of have a map of where you're going. Meaning, I now can identify all my terms. I have a constant term, and I might say, okay, here's my constant. It's now, in terms of its magnitude, that's 20 times the log of 250. And I could just plug that into my calculator if I wanted. But if you're wanting to think your way through that, that's actually 2.5 times 100. The reason I did this is now log of 100 is 2, and this is close to the log of 3, isn't it? Or the log of 2. It's between those, and I know where that is. Log of 2 is 0.3, and log of 3 is roughly 0.5. So I'm somewhere between 0.3 and 0.5 with this, and if you compute it, it's actually 0.398. So now you're at 2.4 times 20, or this 250 gain constant. That's not the DC gain, is it? What's your DC gain? Undefined. It's infinite, isn't it? Because of that pole at the origin. But you do have a constant that's raising everything by 48 dB. And it's 48 dB for all omega. And what's the phase of that constant? So you could even forget that one and you probably wouldn't lose points, but it's a nice idea to write it down. Then you have the pole at the origin. So there's one of my just descriptions of one of the pieces of the puzzle. And how many pieces do I have? A constant, a 0, and 3 poles. And one of those poles, which is really the first one to worry about, is this pole at the origin. And what's its magnitude? It's always on, isn't it? It never breaks. It's always sloping. It's minus 20 dB. I only have one, so it's minus 20 dB per decade. But now where do I pin that on the plot? So now just go back to your birthday party where you pin the tail on the donkey. Now that tail is this sloping minus 20 dB per decade line, and you can pin it on the donkey at 0 dB and omega equal to 1. So this sloping line is going through 0 dB at omega equal to 1. And what's the phase contribution of that pole at the origin? What's the pole at the origin's phase? And now if you forget, just remind yourself you've got all sorts of ways of thinking of this. If you now have a pole at the origin and now you're walking up this imaginary axis, what's the angle from this pole to that point, to this point, to this point? Does that angle ever change? It's always a right angle, isn't it? It's 90 degrees. And since it's a pole, it's minus. So your phase is minus 90 degrees for all omega. And you found that, or you reminded yourself because you drew this little sketch of the S-plane plot, for example, if you've forgotten. That's now the second of the 5 terms. The next thing I would probably do is I say, oh, I have a pole at 0.1. What's the magnitude of this guy? I would say it's 0 dB until I reach the break, right? So if I'm just drawing this piece or this factor, I'm 0 dB until the break, and the break is happening right at the break frequency of 0.1 radian per second. And then the phase of this guy, I just like to identify 3 frequencies. I have the low frequency, which is a decade before the break. And what's the angle theta at low frequencies? It's 0, isn't it? Then at the next point of interest, it's right at the break. What's the angle right at the break frequency for this single factor? It's a pole factor. It's minus 45. And then we finally get to where the whole thing, all the phase is now being contributed. So this is happening at 1 radian per second. Theta is now minus 90 degrees. Questions on that? And now we can do exactly the same thing for the other 2 factors. We have one more pole. That's going to have a magnitude of 0 dB until the break. And did I say, oh, until break at omega equal to 0.1, and then we have a minus 20 dB per decade slope thereafter. Failed to write that in the first one. Now we have the same thing until break at omega equal to 2 with slope minus 20 dB per decade thereafter. And the phase, again, we can identify these 3 frequencies. We have 0 degrees. We have minus 45. And then by the time we reach 20, for that factor, it will be contributing minus 90 degrees. Finally, we have our 0, which is at omega equal to 10. So now we have a magnitude that's 0 dB What's the slope after the break? Now it's going up 20 dB per decade thereafter. But that's an adjustment in whatever we were sloping before. And we were going down at 60 dB. Now we kink up a little bit. Now we're only sloping at 40 dB beyond omega equal 10. And our phase not only starts sloping, but it stops sloping. The magnitude, once it starts, it never stops sloping. The phase, we have the three frequencies. We have a decade before the break, which is 1. That's 0 degrees. We have the frequency at the break. And then we have our frequency a decade beyond. And now I have all of the frequency information that I need to start sketching my plot. I go and I find the smallest frequency. The biggest frequency that I have is this guy, and that's 100. So that's sort of that's where everything quits changing in terms of phase. And then I have to go and say, okay, where is sort of my first frequency of interest? And that's now this 10 to the minus 2, or 0.01. So now I need to have my frequency axis at least between 10 to the minus 2 and 10 to the 2, or a 4-cycle logarithmic plot. Now I can sketch. For my magnitude, I can say, here's my 0 dB line. And maybe now I have 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1, and 10 to the 2. And I might need to put in some guidelines. Now I can go back to my verbal description of all of these, and I can say my constant. What was my constant? My constant gave me a 48 dB curve. I can now come down here and I can say, okay, let me draw just a straight line at 48 dB. That's my constant. Then I had a pole at the origin, didn't I? So that's going to go through 0 dB, and then it's going to back off or slope That's due to my pole at the origin. Then I had a pole at 0.1, didn't I? So now I'm starting there, I'm 0, and then I start to go down at 20 dB per decade. Then I had a pole at 2, which is 30% of the distance between 1 and 10. And now I go down 20 dB per decade there. So here at 20, I'm down 20 dB. And finally, I have the 0 at 10. And that's going up like that. Now you have to put them all together. But that's not too bad if you just start at the left and work your way right. You come over here and you go, okay, here is my pole at the origin, and I need to add 40 to what my constant was. Meaning at 10 to the minus 2, I'm 40 plus 48, or I'm at 88. I now go up to 88, wherever that is, is this 40, 60, 80? So I'm way up here at 88. So I would say there's 88 dB. And nothing has happened to change my slope until 0.1. So I'm going down how fast? From 88, how fast am I going down? 20 dB per decade. So I should be at 68 dB by the time I hit 0.1. Is that clear? So now I could draw another line here, or another dot here at 68, and say I'm coming down with a slope of minus 20 dB per decade. Is that okay? Now what happens? Now I have two poles in play beyond 0.1. Now I'm going down at 40 dB per decade. So if nothing else happened in this decade between 0.1 and 1, I would be 40 dB down from 68. So I should be at 28 dB by the time I hit this. So I'm going to say I'm right there, 28 dB. And this should be sloping faster. Then what happens? Well, I'm still sloping at that same rate until I reach 2. This is 1, so that's an octave, isn't it? So how fast am I going down in terms of an octave span of frequency? 2 poles worth, right? And each pole gives me 6, so I'm going down 12 dB in an octave. So 12 less than 28 is 16, meaning by the time I reach 2 in frequency, I should be at 16. And that slope hasn't changed, has it? That should be the same angle or slope. Now what happens? Now I have 3 poles active beyond omega equal 2, which means if I didn't have anything beyond 2 at 20, I would be 60 dB down from 16. Is that clear? And what's the difference if I take 60 away from 16? 16 minus 60. Put it in your calculator. You're probably brain dead by this point on the exam, right? Is it minus 44? So now you're at minus 44 at 20. But you have to realize something's happened before you reach 20, but let's just put a point there to begin with. Where were we? Minus 20, minus 40. We're right here at minus 44. So now we could connect that dot with this dot, knowing full well that when I hit 10, I'm going to have to back off and stop that much slope. Is that okay? But if I didn't have to stop, I would be down here at 44, wherever that was. Let's say this is now right here at 44. But what do I know happens between 10 and 20? That's now sloping at 18, isn't it? So I'm 18 less than 40 minus 44 when I hit 10. What's 44 minus 18? Or I should say minus 44 plus 18. Minus 44 plus 20 is minus 24. I didn't quite take off or add 20. I only added 18, so I'm at minus 26. I'm at minus 26 dB when I reach 10. Is that making sense? This maybe will be clearer when you look at it some other time, but this is now minus 26, and that's now This is now sloping at minus 60 dB per decade. Now what happens? From 10 to 100, where am I going to end up? What's my slope after 10? What's my pole zero excess? Now everything is now in play. I have 3 poles and 1 zero. I effectively have 2 poles. So now I'm sloping at minus 40 dB per decade. I start at minus 26. I better be at minus 66 when I hit 100. And I just keep going at that same slope. Is that clear? Here now I'm at minus 66. And I just keep going at that slope. And this is now minus 40 dB per decade. You can see that it gets a little ugly, but you now kind of know what your magnitude plot looks like as a function of frequency. This is now the total magnitude in dB. What's the phase look like? You thought that was fun. Now let's look at the phase. Actually, the phase isn't too bad, except what do you have to remember about the phase? It not only turns on in slope, but it also, you need to worry about when it turns off, right? Let's just look at the pieces. We now have, boy, we're really getting restless, aren't we? Let's say this is minus 90, minus 180, minus 270, and this is 0 degrees. This is the phase of, whoa, phase of H. Where do we start? Well, we had a pole at the origin, didn't we? The constant gave us 0 degrees. Here's our pole at the origin at minus 90. We had a pole at 0.1. So that's going to give us 90 degrees of phase transition between a decade below that and a decade above that. Meaning it's going to give us this piece. We had another pole at 2. That's right here. But it's going to kick in a decade below and stop a decade after. It's now going to give us something like this for its contribution. And then we had a 0. The 0 was at 10. So it's going to start a decade before that at 1 and stop a decade after that at 100. Now we just have to add all these pieces up. We start here, don't we? Then what I like to do is actually sort of give myself some indicators. I'm going to go down in slope there, but I'm going to turn it off there. I'm going to go down in slope there, but I'm going to turn it off here. I'm going to go up in slope there and turn it off there. Is that clear? I'm going to start flat because of the pole at the origin. Then I'm going to go down. What's this slope? It's 45 per decade, isn't it? So I'm going to go down at 45 per decade until I hit not 2, but a decade before 2, and that's going to be 0.2. Then I'm going to be going down at minus 90 per decade. Until when? This one's going to shut off at exactly the same time this one kicks in, isn't it? So once I hit this point, once I hit 1, I have This one no longer sloping. This one going down. I'm down at minus 45, but I'm up 45. So what's my slope? Flat, aren't I? I'm not sloping once I hit omega equal to 1. Can I start to fill that in before I get lost? Now I'm going down at 45 degrees until I reach point 2. Then I increase that slope. And so I might say, oh, well, maybe here I'm at some angle, maybe minus 50 beyond minus 90. So I'm maybe at minus 140. Then I say I'm going down 90 degrees per decade. So at 2, I would be 90 degrees lower than what I am here. And I might find that spot here. And I would draw that line until I intersected with 1, and then I go flat. Is that making sense? So I come here and I say, oh, at 20, I would be 90 degrees below that, and I would come down and try to hit that, except I don't get that far before everything starts shaking again. And when it shakes again, now I'm going flat. And I go flat until this pole quits sloping down. When this one quits sloping down, what do I have left? I now have this pole, this 0 going up. So I better come up until I reach 100 in frequency, and I should be at minus 180, which is where I should have terminated. So once I go here, now I'm coming to that point, and that's now my slope. That's now my phase curve for that Bode plot. Questions on that? That's how you combine all of these different factors. Pardon? I'm not quite sure what you're saying, but you should just make a continuous curve. You shouldn't have to be making these 180-degree jumps or 360-degree jumps. I don't want you to do that. MATLAB might do that occasionally, but usually you want to have this smooth transition in phase. Questions on that? I'll leave you to your own for convolution. We've probably had enough. Thank you. Good luck. And I'll see you Thursday for the exam, if not before in office hours. Oh.
I don't know. Like, is that fun? We do that? Or you want to?
I just